How did the CIA and Mossad succeed in locating the hidden compound of Iran's supreme leader? It all began early in the morning, around 8 a.m. American intelligence agencies started tracking movements of several high-ranking Iranian officials inside a key building located in central Tehran. Soon after, a crucial piece of intelligence was passed on to Israeli forces. For several months, both sides had been silently penetrating Iranian communication networks, relying on advanced low-Earth orbit surveillance systems operated through space-based assets. But executing a strike of this magnitude was far from easy. The first phase required disabling a significant portion of Iran's air defense grid. This operation was essential to open a clear path for a large-scale aerial assault involving nearly 100 Israeli fighter jets. However, the target zone was among the most heavily secured areas in the country. So, the question remains, how do you eliminate a target buried deep beneath reinforced structures? The answer lies in specialized bunker-busting munitions. These weapons are designed with delayed detonation, allowing them to penetrate layers of hardened concrete before exploding. This is only the beginning. How exactly did Israel and the United States manage to assassinate one of the most heavily protected men on the planet? The answer? An unprecedented joint operation. For months, the CIA and elite Israeli units waged a shadowy intelligence war. Using a web of surveillance satellites, intercepted communications, and highly placed human assets deep within the regime, they painstakingly mapped Ayatollah Ali Khamenei's every movement, security protocol, and daily pattern. The vulnerability? The Pasteur Street Summit. This would still allow for sharp maneuvers during flight, far beyond what older ballistic models could manage. These kinds of mid-air changes wreak havoc on systems like Israel's Arrow 3 and the US-developed THAAD, which are built to predict and intercept based on expected flight paths. Additionally, there's speculation that the missile may have taken a lower-than-usual flight route, potentially slipping under the radar coverage that usually defends against high-altitude threats. This is the Houthi Palestine II. It was used for the first time based on Iran's advanced missile systems. Inside this missile is a hypersonic glide vehicle which detaches and allows the missile to maneuver and glide at speeds between Mach 5 and 16. The missile has a range of around 1,500 kilometers, only slightly more than its predecessor, the Palestine I missile, or Fatah I. What sets it apart from other ballistic missiles is its ability to accelerate outside the Earth's atmosphere, while its aerodynamic control surfaces enable steering to evade the famous Arrow missile defense system made by Israel. The combination of extreme speed, sudden course changes, and possible stealth capabilities revealed a major vulnerability even in one of the most heavily defended airspaces in the world. What this incident really drives home is that non-state actors are now gaining access to highly advanced weaponry that was once thought to be the domain of major powers. Yemen Houthi militant possessing a hypersonic missile represents a significant threat to both Israel and the United States Navy ships. To understand how the Houthi hypersonic missile works, we need to examine the functioning of Iran's missile technology and Israel's aero defense. Let's study how the Houthi follows the same strategy as Iran when it hit Israel with almost 180 number ballistic missiles. These missiles traveled more than 1,000 meters from this valley to reach Israel's most populated city and military sites. Iran used variants of the Shahab-3 ballistic missile in its latest attack on Israel. The Shahab-3 is the foundation for all of Iran's medium-range ballistic missiles and uses liquid propellant. It can carry a warhead weighing between 760 and 1,200 kilograms, which translates to 1,675 and 2,645 pounds. How it works. Step 1. The missile is positioned at a 90-degree angle and then fired. Step 2. The ballistic missile's trajectory takes it outside or near the edge of Earth's atmosphere. Step 3. The warhead payload separates from the rocket that carried it aloft and re-enters the atmosphere, descending towards its target. Step 4. The missile can carry a single or multiple warheads, depending on the variant. The warhead separates from the single-stage rocket after it has traveled more than half the distance to its target. The most prolific Scud variants had a circular error probable of 300 to 450 meters. This means that 50% of the missiles fired at a target would land within a circle of that diameter. Now let's take a look at how the Israeli defense system works. The Israeli defense system consists of 3 tiers. First up is the long-range aero missile defense system, which was designed specifically with Iranian missile threats in mind. Each interceptor costs several $millions, and they are capable of engaging targets outside the Earth's atmosphere, providing an additional layer of protection. The second layer of defense is the David Sling system, designed to intercept incoming missiles and drones. Finally, the Iron Dome stops most short-range rocket attacks in Israel. Let's take a look at why the Iron Dome failed to intercept the Iranian ballistic missiles. Apart from discussing the multi-layered missile defense system, the Iron Dome itself has a range of around 40 miles, while the David Sling can intercept ballistic missiles up to a range of 180 miles. The top-tier aero anti-ballistic missile systems can target threats up to 1,500 miles away. According to reports, 180 ballistic missiles, which are possibly hypersonic, as claimed by the Iranian Revolutionary Guard, were launched. Although the Aero missile defense system successfully intercepted many missiles before they reached Israel, many still got through. The primary challenge in interception begins once the glide vehicle separates from the missile. After detachment, this vehicle can repeatedly alter its flight path, making it extremely difficult for systems like the Aero interceptors to accurately track and engage it. This maneuver also bypassed the David Sling and finally the Iron Dome system, which is not designed to counter hypersonic missiles like the Fatah II model. Let's examine the cost implications of a single day of missile attacks. Iran expended over $200 million by launching ballistic missiles along with drones, whereas the IDF spent $1 billion to defend itself. This includes the Aero missile, which costs around $2.5 million. The David Sling costs around $1 million to produce, while the Iron Dome costs around $20,000 to $100,000 for a single missile, depending on inflation. By contrast, Iranian ballistic missiles cost around $200,000 each, and its drones only $20,000 to $50,000 each. The Aero missile defense system consists of 3 basic parts: the missile launcher unit, the Green Pine radar antenna, and the Aero missile. The missile launcher unit is composed of 6 erector launcher tubes housing ready-to-fire missiles. Positioned at the rear of a 2-axle trailer, each launcher, when fully loaded with 6 launch tubes carrying ready-to-fire missiles, weighs 35 tons. The Green Pine radar serves as the warning and fire control radar for the A-3 anti-ballistic air defense missile system. It plays a crucial role in target detection and guidance. The Aero operates as a 2-stage missile. Let's look inside this engineering technology. This is the solid propellant booster and sustainer rocket motors. At the rocket's peak sits the ignition chamber, triggering the combustion of the solid propellant when activated. This propellant isn't just any substance. It's a meticulously crafted blend of fuel and oxidizer poured into a casing and then cured. Encasing this blend is a protective shell called the motor case. At the core of the rocket lies the propellant burning zone. Here, the solid fuel and oxidizer react, producing incredibly high-temperature combustion gases, which helps to launch the rocket at incredible speed above the Earth's surface. Moving further to the front, the most important part of the missile is the kill vehicle, which can be divided into 3 basic parts. The second stage consists of the propulsion system equipped with a thrust vectoring control nozzle. Positioned above it is the warhead, a directional, high-explosive fragmentation unit weighing around 150 kilograms, or roughly 330 pounds. The third stage features the seeker system, which can dynamically adjust its orientation to continuously track the incoming target. So, what makes this long-range anti-ballistic missile system so effective? It all starts with the propulsion design. For example, the well-known THAAD system relies on divert and attitude control thrusters. In contrast, the Arrow 3 kill vehicle uses a thrust vectoring nozzle powered by a solid fuel rocket, resulting in a shorter but highly controlled burn phase. One key advantage of this design is its ability to compensate for radar inaccuracies. If the radar initially guides the interceptor slightly off target, the Arrow 3 kill vehicle can correct its path mid-flight. Given the extreme speeds of intercontinental ballistic missiles, the interceptor must constantly adjust based on updated tracking data from its onboard seeker. Even a slight failure to realign with the updated trajectory could result in a missed interception. If you enjoy deep military and engineering breakdowns like this, make sure to subscribe and turn on notifications so you don't miss the next video.